Okay, first topic that we're going to cover in class is the biomechanics of running. I pick that to start off this class because not to imply that running is central to all sports. You can certainly think of sports where running isn't all that important or where running isn't part of the sport at all. But I would say that's fairly rare for most sports that you guys probably think of when I say the word sport. Most sports involve running at least as a key movement that you need to be able to do with some basic level of competency to participate in that sport at any level. There's of course running itself as a sport, road racing, track and field, marathons, etc. But also other sports like basketball, for example, or soccer or football, where running at a submaximal speed is a key element of that sport. You need to be able to at least competently and ably run to be able to participate in those sports, and being a good runner is typically beneficial for participating in those sports. So again, not that running is kind of the central aspect of all sports, but it's certainly a main element of many sports. This first paper that we will cover in running is by Novacheck. It's a review article on the biomechanics of running, as you can see from the title here. If you want to stay caught up in the pace of the class, I'll start a little slow here. So over the course of this first week of class, and then by the end of the second week of class, you should ideally have read through all 10 of the running papers here and watched all 10 of the lectures on those papers on running. So this is the first one here, the biomechanics of running. I like this article because it's a very instructional tone and style. It's targeting individuals like you guys who are maybe interested in the biomechanics of running but don't have a deep knowledge yet of the biomechanics of running. So he does a nice job here of summarizing a variety of kind of the main elements in terms of gait analysis and biomechanics for a movement like running. Touches on a lot of just main elements here for quantifying the mechanics of running. The big thing that I wanted to cover here on this paper was tying back in to something that I emphasize a lot in Kines 300, and that's what can be inferred from the data at the level of joints in terms of what's going on with the muscles that span those joints and control those joints. If you are not a kinesiology major, you will hear me constantly in this class referring to Kines 300. And if you didn't take that class, you might be wondering what the heck's he talking about all the time with Kines 300. Kines 300 is the biomechanics of human movement class in the kinesiology major. It's a core class in the major that all kinesiology majors have to take, and it's an introductory treatment of using principles from classical mechanics and classical physics to explain and study the human body in motion. So if you hear me constantly referring to Kines 300 and you don't know what I'm talking about, that's what I'm talking about, an introductory course on the mechanics of human movement that the kinesiology majors have to take. Now, one thing that I emphasize in that class is what you can infer about muscles from looking at data like this in Figure 9. This is Figure 9 of the Novacheck paper, page 10 out of 19 in the paper, page 86 in the file itself. Okay? Each one of these 9 panels here shows some biomechanical data at one of the 3 joints of the lower limb, the 3 main joints that we think of as being important in running, either the hip joint here in the first column, the knee joint here in the second column, and the ankle joint here in the third column. The top row shows the angles of those joints, so the motions of those joints during running. The middle row shows the moment at those joints, or the kind of net angular force at those joints. And the bottom row shows the power of that moment. Okay? Each one of these graphs is plotted on the x-axis from 0 to 100% of the gait cycle, and then on the y-axis, the magnitude of whatever biomechanical variable we're looking at here in this graph. If you're not familiar with the gait cycle, he goes over it in section 2 of this paper, and I'll give you a quick demonstration of it here. Hopefully you guys can see me in my phony gait lab here. In other words, my kitchen floor. This is what we have to work with here in the time of COVID, I guess. The gait cycle, you can actually quantify it starting from any particular point or event in the gait cycle, but we will typically have the gait cycle starting at heel strike. So imagine here, I'm walking across the floor, and you freeze my gait at the instant when my right heel first hits the ground there. Okay. I'll then proceed with my gait cycle and do a step with my right leg and then my left leg, and then my right heel will again hit the ground again. Okay. My gait cycle, or my stride cycle, is everything that happened between those two consecutive heel strike events of the right leg. Okay. So I'll go backwards in time here. So my right heel hits the ground. That's the start of my gait cycle. I finish my right step, I finish my left step, and then my right heel hits the ground again. Everything mechanically that happened between those two consecutive heel strikes of my right leg, that was my gait cycle, or my stride cycle. So each one of these graphs that you see here in figure 9 is showing these data, these biomechanical data at the hip or the knee or the ankle, from heel strike of the right leg at 0 up until heel strike again of that same right leg at 100%. Okay? These vertical lines here in the graphs are indicating the stance phase, the portion of the gait cycle when the foot's on the ground, and the swing phase, the portion of the gait cycle when the foot is airborne or not on the ground. And you can see in running we spend actually most of the time with our foot airborne. We actually have a period of time where the whole body is airborne, right, where both feet are off the ground. So stance phase relatively short in running, swing phase relatively long. Okay, in the first row here, again, it's showing the angle of the joint. In the middle row, the moment or the angular force at the joint, and the bottom row, the power of that moment. Now, what can I infer from those data there about the muscles that are controlling those motions? The motions of my hip and my knee and my ankle are controlled by the muscles that comprise those joints. In biomechanics, we really like muscle. We'd ideally like to take measurements of muscle forces and muscle strains and muscle energy expenditure and all these things. Typically, we have a really hard time, sometimes an impossible time doing that, because muscles are inside the body and we can't easily access them and put sensors and stuff on them and take measurements from them. We have a much easier time measuring things at the joint level, right? The motion of the joint, the moment at the joint, the power at the joint. Those are things that we can either fairly easily measure or estimate from measurements with mathematical modeling and calculations and some fairly reasonable assumptions. Okay? So we have a lot easier time quantifying what's happening at the joint level than we do at the individual muscle level. But we can still say something about muscles from these joint level data by understanding mechanically the relationship between joint kinematics and kinetics and muscle kinematics and kinetics. And what am I getting at there exactly? Let me show you another example with my video here. Okay, and I'll probably need a chair to do this. I can't hold my leg in the air long enough. But here, hopefully you guys can see my knee joint of my right leg. Okay? And my knee joint is spanned by my knee extensor muscles, my quadriceps, on the top of the joint there, and by my knee flexor muscles here on the other side of the joint. Okay? Again, my knee extensors are my quadriceps. They run down my thigh here and run into my kneecap, and then the kneecap kind of collects all those forces and expresses them across the patellar tendon there, and then that tendon will sustain the forces produced by these 4 quadriceps muscles. And if I take the force in that tendon from all 4 of those muscles times the distance between that tendon's line of action and the center of my knee joint there, that distance is the moment arm for that tendon. And if I take that distance times that tendon force, right hand rule, that gives me a extension moment of the knee. So this is why my quadriceps are my knee extensor muscles. When I fire them up and produce force, they produce an extension moment at the knee, which moves it in the extension direction. Okay? Similar story in the other direction. I have my knee flexors, primarily my hamstrings, and also my gastroc muscle on my calf there has a a knee extension or a knee flexion moment. When I fire up those flexor muscles, their tendon forces times their distance to the center of that joint from right hand rule gives me a knee flexion moment that flexes that joint there. Okay. So that demonstrates one thing that we can infer about muscles from the joint level data here. The sign of the moment on the joint can tell me what muscle group is primarily responsible or is primarily producing force at that time. Here at my knee, for example, if it's a knee extension moment, then my knee extensors, my quadriceps, are primarily producing force at that time. If it's a knee flexion moment, here in the late swing phase, then my knee flexors are active, my hamstrings and my gastrocnemius producing force at that time. If I look here at my hip, in my middle of my stance phase or towards the end of my stance phase and early on in swing, I've got a knee or a hip flexor moment. So my hip flexors, my rectus femoris and my iliacus and my psoas muscle, those are primarily active at that time or producing that force. If it's an extensor moment here in late swing or here in early stance, then my hip extensors, my glutei and my hamstrings are primarily active at that time. So direction of the moment tells me something about what muscle group is producing force at that time. Okay, back to my video here. You can also infer kinematics of the muscles from the motion of the joint. Notice here that when I'm extending the knee joint, because my quadriceps wrap around the top of the joint, as I extend the joint, my quadriceps get shorter, right? The further that I extend the joint, the shorter those muscles get. Okay? And then on the other side of things, the further that I extend this joint, the longer my flexors, the longer my hamstrings get. Okay? And then opposite story in the opposite direction. As I flex the joint, my flexors get shorter and my extensors get longer. Okay? So from the direction of the joint motion, which you can reason out here from the joint angle, you can reason out what's happening to the length of the muscle groups involved, whether they're stretching or whether they're shortening. So moment tells me which muscle group is active, and angle can tell me something about how that muscle group is behaving kinematically, whether it's stretching or whether it's shortening. If I combine these two pieces of information, if I take these joint positions and if I differentiate them to get the joint velocities or joint angular velocities, if I then take those velocities times these forces down here, take angular velocity times angular force, then the product of those two things gives me power, right? Mechanically, power is force times velocity. So if I take these velocities, which I determine from these positions, and multiply them by these moments here, then I get the power of those moments. Now, just like or not just like, but similar to how I can infer what muscle group is active from the sign on the moment, the sign on the power can also tell me something about that muscle group. If the power is positive, then it indicates whatever muscle group is active up here is acting concentrically, meaning it's producing force while the muscle is shortening. If it's active with a negative power, then that tells me that muscle group is acting eccentrically. It's producing force while the muscle is lengthening or while the muscle is being stretched. Now, why is that important? Why is it important to know whether the muscle is producing force while it's lengthening or producing force while it's shortening? That is important because of this relationship that you'll get real tired of if you take Kines 300 with me, because I harp on it constantly, this force-velocity curve of muscle. If you haven't seen this before, this is a really important relationship in human movement in general and in muscle mechanics and biomechanics specifically. This is the relationship between how much force a muscle produces versus its velocity of contraction, whether it's shortening quickly or whether it's lengthening quickly. And you can see here that for a muscle that is shortening, if it's being shortened quickly, the faster the muscle shortens, the less force it can produce for a given activation level. But if we're lengthening the muscle, if it's doing an eccentric contraction, it's the opposite story. Up to a certain limit, the faster that you lengthen the muscle, the more force it can produce. So generally, if your goal is to produce forces with muscles economically, it's a good idea to activate those muscles at times where you can put them up on the eccentric limb of this force velocity curve, where you can produce a lot of force for a given activation level of those muscles. And is that what we see in running? Not always, but it is what we see a lot of the time for a lot of the major extensor muscle groups in running. And that is indicated here in the last thing that I wanted to cover in this paper, and that's figure 4 here. These are data from the timing of when muscles are turned on and off by the nervous system in running, as indicated by EMG data. If you haven't heard of EMG before, EMG stands for electromyography, which sounds like a fancy word, but it's really just 3 words that you know already. Electro is electrical. Myo is a fancy word for muscle. And graphy means graphing or visualizing. So electromyography is simply visualizing the electrical activity of muscles, or visualizing the control signals coming from the nervous system to the muscles, asking the muscles to activate and produce force. We measure these electromyography or EMG signals in biomechanics by placing sensors on the skin above the muscle, or sometimes by inserting little instrumented needles into the belly of the muscle. And this can give us an idea of when the nervous system is asking muscles to activate and produce force in a movement like running. And you can see here in the timing of when muscles turn on and off in running that, with a few exceptions, the main extensor muscle groups, the hamstrings of the hip, the gluteus of the hip, the quadriceps of the knee, the gastrosoleus, the plantar flexors of the ankle, they all tend to get activated towards the end of the swing phase and then be active during the heel strike event of the gait cycle. Okay? Now, why is that a good thing? Why is it a good idea to try and activate my extensor muscles, my hip extensors, my knee extensors, my ankle plantar flexors? Why is it a good idea to have those active around heel strike when running? I'll try and demonstrate this for you here in my video. So you guys should hopefully here be able to see my right hip and my right knee and my right ankle there. Okay? Now, when I do my heel strike event, let's pretend I'm running here. When I do my heel strike event, my right heel hits the ground there. And let's see what would happen if I turn off my hip muscles, and if I turn off my knee muscles, and if I turn off my ankle muscles. If my muscle groups are all just quiet there and inactive, then I hit the ground, and gravity just pulls me straight into the ground, and I collapse, right? I fall over. So when I hit the ground with my heel, what I want to do is I want to prevent the hip from flexing. I want to prevent the knee from flexing. I want to prevent the ankle from dorsiflexing. I do that by firing up the muscles on the other sides of those joints, right? I fire up my glutes so that I resist this motion with this motion. I fire up my knee, or my quadriceps, so that I resist this motion with this motion. I fire up my plantar flexors so that I resist this motion with this motion. Now, generally, gravity, at least in the early part of the stance phase, right after heel strike, still wins out. You'll still see the heel hitting the ground and the whole body doing this, at least briefly, but you'll be activating this muscle group, activating this muscle group, activating this muscle group to resist that motion, and then get ready to push off the ground with those muscles later on in the gait cycle there. Now, notice here what's happening when my heel hits the ground. And when I flex my whole leg down like this, I'm stretching my glutes, I'm stretching my quadriceps, and I'm stretching my plantar flexors. So by stretching those three muscle groups, I'm putting them up on that eccentric limb of their force velocity curve and putting them in a spot on that curve where they can produce a lot of muscle force for their given activation level. So generally it's a good thing that we activate those big, strong extensor muscle groups there around heel strike, because due to the mechanics of running and the presence of gravity, those joints are going to be flexing around that time, meaning it's going to be stretching those big, strong extensor muscle groups. And by activating them at that time, I can produce a lot of force with those muscles for a given activation level at an economical level of effort and energy expenditure. So in other words, I just kind of get a lot of bang for my buck there. I can produce a lot of force at a reasonable level of muscle activation, and then have those muscles primed and ready to produce a lot of force later on in the stance phase when I then want to push off the ground and propel myself forward. Okay, that is really all that I wanted to emphasize and highlight in this paper here. Take a look at the whole thing. It's a pretty dense paper. There's a lot here, probably a lot of new stuff. You may not necessarily understand all of it, like when it gets into some of the more complicated things here at the end about like economy and biarticular muscles and tendons as springs as whatnot. These are all things that we will touch on a little bit later on in more specific focused papers in class on those things. But this is just kind of a nice superficial intro to a lot of the relevant biomechanics of running. Okay, that is it for this one, and we will see you next time.